Hello, and welcome to our last Ask a Physicist of this semester. As always, I have a few reminders. Tonight, we will get to questions towards the end of the talks, but if you have any questions at any time, you can submit them using the Q&A feature at the bottom of your Zoom window. This webinar is being recorded and we will post it to our Beyond Center YouTube channel later on this week if you want to watch it again or share it with anyone that you think might be interested. Tonight we have Cole Mathis joining Ask a Physicist as a moderator. Cole is a physicist and NASA astrobiologist. His research focuses on detecting life on other worlds and understanding the origin of life on Earth. So I will go ahead and turn it over to Cole.
Great, thanks, Jessica. Thanks everyone for joining us. I won't say too much. Maulik is a regular here, and he's going to start us off with a conversation about what is reality, which is the title of this sort of session. And I think he's going to walk us through some surprisingly simple arguments that emerge from understanding quantum mechanics and lead to fairly deep questions. And then he's going to hand it over to Paul, who will take us in a slightly more speculative direction, I think, but interesting nonetheless. And then we'll have some questions. So Maulik, over to you.
Thank you. Cole, can everybody hear me? Great. So I'll start sharing my screen. Hold on. Here we go. So the title is this provocative and somewhat vague question: what is reality? And there are many ways to answer this question or to approach this question. It's a question that's been asked by philosophers and physicists and science fiction writers. And we've touched on this in the past when we talked about whether we live in a computer simulation. And I think Paul is going to take a little bit more of a metaphysical or broader view on this question. But I'm going to hew very closely to the physics, to actually very conventional physics, and tell you basically what we learn about the nature of reality from quantum mechanics. And the answer is absolutely bewildering and staggering and unexpected and confusing. And I won't have any clear answers at the end because we don't really have a clear understanding of what's going on, but I'll just present to you what it is that we've learned from 100 years of quantum mechanics. So before we get to that, let me tell you about the world that you know about, the world of the classical world. The classical world is the world, the non-quantum mechanical world, the world of our everyday experience. So this world is highly predictable. So what that means is, here's a rather romantic portrait of Galileo doing a gravity experiment where he's dropping two objects from the side of the Leaning Tower of Pisa. And if you were to do this experiment, then the ball or the stone or whatever would land at the ground in about 3.37 seconds. That's by my calculations, if you neglect air resistance. If you do include air resistance, you can calculate it as well. That's something I do with my undergraduate students. And so the key thing here is that no matter how many times you do the experiment, you're going to get exactly the same answer. Okay, and so it's almost it's like overkill to do this experiment, too many times. And what that indicates is, what that seems to indicate is that there are elements of reality that one can maybe attribute as a result of these definite observations. So for example, the fact that this is happening again and again in a predictable way might encourage you to say that it is true, it is an element of reality, it is real that the stone exists and has an initial position at the top of the tower, and then it's subject to gravity from the Earth, and then that stone then follows a downward trajectory, and you can say once you know its motion, where it is at every instant of time. And finally, the stone arrives at the base of the tower as its final position. And it does all that in 3.37 seconds. So you would say that those aspects are true in some sense. And I want to emphasize that this is not just about physics experiments. This is about our world. Remember, whenever we use technology or anything, what is a physics experiment? It's just a way of interacting with the physical world. Whenever we do anything that interacts with a physical world, whether it's sitting on a chair or opening a door or pressing start on a microwave, all of our use of technology relies on the existence of definite predictable outcomes. The world would be a very different place if random things were happening all the time. So we are really, really accustomed to a world in which things seem to exist and are reliably there and are definite and predictable. Okay, so that's the classical world. But before we leave for the quantum world, I want to say that there are actually some instances where we are not able to make definite predictions. And so an example might be a coin toss, right? So when you flip a coin, that's not something definite. So there's a 50-50 chance it'll land heads or tails. So what's going on there? Well, the way to understand this is, in fact, the coin toss is completely predictable. If you were to take into account the exact way you flip the coin, the angular momentum you gave to it, what the air currents are doing, what the mass distribution of the coin is, then you would be able to predict with 100% certainty exactly how the coin would land. It wouldn't be a matter of chance whether it's going to land heads or tails. It would be a matter of definite predictable. It would be a definite, something definite. So in other words, the appearance of probabilities, the appearance of chance for a coin toss is merely a result of the incomplete information that we generally have about coin tosses. We're not really paying attention to the precise way in which it's flipped, and so it looks random to us because we can't. But if we were keeping track of everything, if we had a full theory of the coin, then there's no element of chance in this at all. The same goes for the weather. The weather, we say there's a 30% chance of rain, or in Arizona, there's a 1% chance of rain. But that may appear like it's probabilistic, but in fact, the weather is completely predictable. It's only because we're not taking into account exactly what everything is happening, what's going on with the weather, what that butterfly in China is doing that's flapping its wings. So because of that, we aren't actually able to predict the weather fully, and that's just, again, an instance of our having an incomplete theory. All right, so that is the quantum world, and this thing about how you might have heard of chaos theory, which basically says that some little errors that you might have because you didn't measure something with 100% precision can get amplified and lead to big errors down the line. Okay, now I want to tell you about quantum mechanics. So here is this beautiful picture or video of an electron around a hydrogen atom, and this is in the 3-2-1 orbital state, it's called. And the electron so the colors have a meaning in terms of the phase, but that's not important. The important thing is the electron is just a point, but here we have this kind of cloud. And what this cloud is telling us is where the electron is likely to be. So where it's dark, that's where you're not going to find the electron. So for example, you won't find it right at the center or far away from the center. But wherever they're sort of brighter, that's where you're most likely to find the electron. So for example, if you were to do an experiment and actually look for the electron, you might find here in experiment 1 that the electron is in some place within the cloud. Like experiment 2 will give it somewhere else, and so on and so on. So this looks very different from the corresponding situation for the stone dropping from the side of the tower, because there we got the same result every time, and here we seem to get this variety of results. So there are two questions we can ask because based on this. One is, what is the electron doing when we're not looking at it? And the second question is, why are we not able to exactly predict where it is? Okay, so let's answer them in turn. So what is the electron doing when we aren't looking at it? So we're sort of periodically probing where the electron is, maybe by shining a light on it, and so it's a little bit like this. Maybe something is happening like this dancer in the stroboscope. We're periodically checking to see what they're doing, but they're sort of just moving around randomly. But in this case, the dancer has a definite trajectory, has a definite location, even when we're not looking. Okay, so the dancer is certainly there, but we're only seeing them looking at his position once in a while, and so it looks like a sort of jerky motion. And but why is it that we can't actually predict exactly what the electron is doing? And so maybe the reason we can't predict the precise location is that we're missing some key information about it. So that would be very much like a coin toss. In the coin toss, we can't say exactly what the coin is doing just because we haven't kept track of all the physics of the coin. So maybe we're missing some of the physics of the electron, and that's why we can't make a definite prediction. And so this idea is called hidden variables, that there are some hidden variables that we haven't taken into account. And if we only knew what those variables were, or if we were taking into account, we would be exactly able to predict what the electrons do. However, in 1964, which is very late in the day, if you think about it, quantum mechanics was from early in the last century, J.S. Bell realized that there was actually an experiment one could do to test whether or not this theory was complete, whether or not quantum mechanics was a complete theory. So the experiment is a little bit difficult to describe. There's some subtle correlations you can have between multiple experiments. But Bell realized that if quantum mechanics was a complete theory, you'd get one outcome, and if it was not, then you'd get another outcome. And experiments were done, and they confirmed that quantum mechanics is a complete theory. Unlike the theory of the coin, we're not missing anything. This theory is the correct full theory of the electron, okay, at least in terms of local hidden variables. Now, that is a shocker, because here's what it means. If quantum mechanics is complete, then the electron is fundamentally governed by chance. It's not governed by chance in the fake way that the coin was governed by chance, because the coin was only governed by chance because it was an incomplete theory. If this is the complete theory, then the electron is truly governed by probability, by chance. And therefore, there's no way to predict with certainty where it is, because it's a probabilistic theory. You can't. And that means that when it is not being looked at, it has no definite location. Let's just visit this, follow these steps again. If the electron had a definite location, then we will be able to predict with certainty where it is. We'd say it's right here. So the fact that we cannot predict where it is, even in our complete theory, tells us that it doesn't have a definite location. The electron you can think of is like an unflipped coin in your pocket that's neither heads nor tails. It has a potential to be heads or tails with a 50-50 chance, but at that moment, it's actually in a cloud of possibilities where it's neither heads nor tails. And in this way, an unobserved electron simply does not have a location. That's not an element of its reality. It's like that old story where you say, if a tree falls in a forest and no one's there to hear it, did it actually fall? Well, quantum mechanics says that not only did it not emit any sound, but there was no tree and no forest either. Albert Einstein hated this theory and spent his lifetime trying to find loopholes in it or to find a flaw in it. In fact, even on his deathbed, he was trying to find an alternative to quantum mechanics. He says, that do you really believe the moon is not there when you're not looking? Because whatever applies to the electron also applies to other objects. And he wrote to his friend that in that case, I'd rather be an employee in a gambling house than a physicist. Okay, so finally, I just want to say that this is very alarming that there's no reality. And so people have proposed different interpretations, and one of them is the many worlds interpretation of quantum mechanics. And in this picture, every possibility is realized. So in this case, the electron does have a definite location, but the price to pay is that it has a different one in each of an infinite number of worlds. And we'll probably have more to say about many worlds in the question session. So let me end here with. There
was a time when the newspaper said that only 12 men understood the theory of relativity. I don't believe there ever was such a time. There might have been a time when only one man did, because he's the only guy who caught on before he wrote his paper. But after people read that, a lot of people kind of understood the theory of relativity in some way or other. But more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics.
Thank you.
Great, thanks for that, Maulik. Paul, we'll hand it over to you now.
Hello, everybody. Thanks for joining us. And let me start out by saying that my ghostly pallor is not my real color, which is a bit closer to that. And it shows how our senses can deceive us. And so I'd like to start, once I can bring up my PowerPoint, like to start by telling you what I'm not going to talk about. You probably can't see that because I didn't do the screen share. Just a second. I think by now we would know what to do with all these things. Share screen, share. I hope you can now see Descartes' demon.
We can.
Good, right. So the purpose of showing you that is that philosophers have long wondered about the nature of reality. Is there a world out there? Or could it be that some malicious demon is fooling us into thinking that there's a world there by feeding our sense organs, sensory data that is fake? In other words, that our impression of a world out there of reality is actually a fake. In recent years, this has become known as the simulation argument, because it now seems plausible that you could build a super-duper computer that would have, in the not-too-distant future, have some sort of element of consciousness. And so this super-duper computer might be inhabited by virtual beings who could be fed a virtual world, and for them this would be a fake world. Now, I'm not going to talk about that. So I know a lot of people have been sending us questions about the nature of consciousness, saying, can we rely on our senses and all of those things. And the reason I'm not going to talk about it is because we did an earlier Ask a Physicist on the simulation argument. So I want to pick up actually where Maulik left off and talk a little bit about quantum mechanics. So reality before about 1900 was pretty straightforward. It consisted of, there was a world out there. I'm assuming there is some sort of world out there, even if it's a weird world. But before 1900, people thought, well, there's space and there's time and there are particles. And the particles were regarded as like scaled down versions of billiard balls or baseball balls, which is what you see here, or even for some of us, cricket balls. Doesn't matter. The whole idea was that it was just everyday type of things writ small on a very small scale, but they were sort of really there. And as Maulik has been explaining, people thought that that even if we lack the ability to discern it, if you ask where is an electron, or you identify a particular electron going around an atom, where is it now and how is it moving? And even though we may not know the answer to that, it was assumed that it was a sensible question to ask. So reality was very close to the sort of everyday common sense version, but at the atomic level just scaled down. Now, there's a misconception about quantum mechanics. A lot of people say quantum mechanics says that the matter is unreal. It's not out there at all. And that's not true. What I would say is that something like an electron is less than real, if by real we mean the 19th century version of that. Again, as Maulik has explained, if I choose to do an experiment to measure the position of an electron, I will find an electron with a position. If I choose to measure the motion of the electron, I will find an electron with a speed or momentum. I have to decide which of those experiments to do. You can't do both together. So there is something there before I do the experiment, but it's not concretized. And the act of doing the measurement brings into existence an electron at a place or an electron with a speed. And somehow it's up to the experimenter, or maybe some automatic system that has been set up to determine the nature of reality at that moment. But if you ask, well, what was the electron really doing before I chose to measure this or that, it has no answer. And I think Maulik has explained that very well. But it gets worse than that. So just to be a little bit technical for the professional physicists, so the state of, when we used to talk about the state of the world before about 1900, what you meant was a point in a 6n dimensional phase space. That is just saying that any given particle will have a position, requires 3 numbers in 3-dimensional space, and a momentum requires 3 numbers. And so in this 6n dimensional space for n particles, that was reality, and it was completely deterministic, again, as Maulik has explained. Today, we have a very different interpretation of the state of the world. Technically, we would say it's something like a vector and an infinite dimensional Hilbert space, a very abstract thing. So before 1900, it was just a common sense view of the nature of reality. It was like everyday reality, but scaled down, if we're talking about atomic dimensions. But today, we've got some very abstract notion of what is out there, of the state of the world. And again, I emphasize, I am assuming that there is a world out there, even if it's a rather weird and nebulous one, that there is something there, but it's rather abstract in the way we describe it. Now, it gets only worse because I've been talking about particles, but when we apply quantum theory to fields, like, say, the electromagnetic field, then we interpret a particle, say the photon, as being a quantum of the mode of vibration of the electromagnetic field. So imagine a guitar string and you pluck it. You pluck the different strings, they have different frequencies. Even technically, for a guitar string, if you apply quantum mechanics to it, it can vibrate with only certain discrete energies. And if you say, well, what is a photon? It's actually a mode of excitation of an electromagnetic field. So it's sort of spread out. If you imagine a big box and you've got the field obeys reflecting boundary conditions in the box, then the excitation, the modes of those fields are the photons. So that it's not like a little particle that you can tie down somewhere. And that leads to some really weird effects when you think of it as being smeared out. And very formative influence upon me when I puzzled over the nature of reality many, many decades ago. Back in 1974, I did a calculation that showed that if you undergo uniform acceleration, it looks like you're surrounded by a bath of heat. So think photons, but all particles would be there. And what it means is if you're accelerating through a vacuum, through otherwise empty space, if you're accelerating through a quantum state which to somebody who is just sitting still would just look totally empty, you see a bath of photons with a thermal spectrum, bath of heat. They don't. So who's right? Are these photons really there? Well, Bill Unruh did a very nice calculation with a model particle detector that was undergoing uniform acceleration. And he found that, sure enough, in a vacuum state, that is in a state totally devoid of any photons, any particles, it would go click, click, click. It would register the presence of a bath of heat radiation. That is, that the particle detector would detect photons if it was accelerating, but not if it was not accelerating. So are the photons there or aren't they? Well, it's an aspect of quantum mechanics. It depends what you choose to measure. And so when we talk about a universe with particles, it's really a very shorthand way for saying the particles are what particle detectors detect. And you can't say what's there or what isn't there unless you specify exactly what the particle detector is doing, how it's moving, and you can talk about the state of the world, but to say there's a particle there or a particle detector has been detected depends very much on the way the detector is moving. So let me I just want to wrap this up very soon, but a part and parcel of this notion that there is a world out there, it has a state, but it's a very abstract state. That state evolves according to some laws, the laws of physics. We don't know where the laws of physics come from, but we assume that they are mathematical relationships. Now, this is where arguments break out over coffee in physics departments, because physicists who are working on really useful things, like trying to develop new materials and so on, will often think or regard the laws of physics as convenient ways of cataloguing our observations of the world. So there are facts of the world, and we need to stitch them together, and laws of physics are a very good way of doing that. But if you work in rarefied areas like string theory or foundations of cosmology or quantum field theory and so on, you tend to find that physicists think of the laws as really there, as actual real things. I've had conversations with colleagues where they make that precise point. They say, well, the laws we've got in the textbooks are only approximations to the real laws, but there are real laws out there somewhere. And these laws are infinitely precise mathematical relationships, and they somehow form the bedrock of reality. So there's a great chain of being then, which starts with mathematics, and the laws of physics are mathematical relationships. And when we talk about, the universe and matter and all that sort of stuff, well, that is something which is derived in this abstract way that I've been describing. And then to go on beyond that, we get to more complex things like life and mind and consciousness. But for physicists working on these foundational questions, it's really mathematical laws of physics are the bedrock of reality. That's what the universe is. So I call this like the great inversion, because I think many people would feel that the most primitive aspect of our experience is our own observations, and that goes back to Descartes. But the observations, because of quantum mechanics, are quantized, so we get bits of information from those observations, and then from those bits of information we stitch them together to form mathematical laws. And then, as I've described, matter, space-time, and so forth are just abstract constructs. So here we have this great inversion that before 1900, the world was real and the laws of physics were abstractions. But today, at least among the people working on these foundational questions, the laws themselves are the bedrock of reality, and the world, the state of the world, that is an abstraction. So it's turned upside down. And do I really believe this? Well, I certainly used to believe it. Maybe for 20 years, I was really caught up with this way of looking at the world. It's a position sometimes called Platonism, the idea, going back to Plato, that mathematics really exists in an abstract realm. It's out there somewhere. And I felt the same about the laws of physics, infinitely precise mathematical relationships, which we are zeroing in on, haven't maybe got there yet. And that is the bedrock of reality. And the rest is all just abstraction and construction put on top of that. I think I've changed my mind in the last maybe 20 years. I think I've come to the point of view that the laws of physics are idealizations, and I'm not sure that we can trust those idealizations. I think there may be flaws in the laws. I'm not going to say any more about that because it's a whole different topic, but I wanted to put out there the idea that quantum mechanics leads to this strange reality inversion. So I think I'll stop there and we can move to the questions. So I'm happy to get Maulik's reaction if he thinks it's just a load of baloney.
Yeah, I think that would be great, actually, Maulik, if you have any response to this sort of idea of this great inversion, or if you find that maybe there's even been some changes since then. I know that there are some theoretical physicists that if I push them, they would say, well, yeah, these, the world is, and these abstractions are sort of useful constructions. And I know some material scientists that have to do things in the lab and make reactions happen. And they say, well, the laws of physics are just there. What do you mean this is an abstraction? Like that's the real thing. Everything else is noise away from that. So I'm not sure if you have any comments there or any reaction to what Paul said.
You're on mute.
Yeah. I guess it depends what you mean by laws. In string theory, there's this idea of the multiverse, and many of these multiverses have their own laws of physics. They have electrons, they have different forces, different particles, different masses for the particles, and so forth. And so the worlds you would encounter in these, you wouldn't have stars in some of them. You'd have but still, in order to describe all of this, you need a theory that's sort of meta enough that it can include all these different worlds which have their own laws of physics. So then you might ask, well, isn't there something even more meta than that? And so Max Tegmark has sort of these, I think Paul likes to talk about this, different layers of abstraction in which somehow almost any consistent mathematical structure is a possible world. I think that's a little bit, for me, that's a little bit hard to swallow. Yeah.
But let me just throw
it becomes
in
semantics, I think.
As a comment, because I think your position, Maulik, would be very similar to most of our colleagues. It would be a bit hard to swallow. There are only really two natural states of affairs when it comes to laws. Either nothing exists or everything exists. If less than everything exists, then we have the problem that there's a boundary between all those things that are possible and actually exist, and those things which are possible but never got around to existing. What Stephen Hawking said, what is it that breathes fire into the equations and makes a universe for them to govern? All these other Poor equations didn't get fire, breathed into them. Well, what is that fire-breathing entity, and who makes that choice? So I don't think we should go down that path in this particular discussion because we've got lots of questions. But
in general, just as there's this story of turtles all the way down, it's also questions all the way down. So even if we get to the ultimate laws of physics, we'll always be able to ask why these laws. And
right.
I think,
right.
Yeah, I don't know.
Perhaps we should take some questions. Cole.
Yeah, so I think it would be great to get some questions, especially since this is Ask a Physicist. So we should give some people a chance to ask the physicists that are here. Just before we do that, I want to remind everyone, if you have questions, still you can throw them in the Q&A section. There's 3 there now, and we received some earlier that I'll start with. Just before I do that, I want to get a reaction from Paul and Maulik about another thing that would cause fights over coffee in physics departments, which is you both mentioned that this property of quantum mechanics, that somehow the observation determines sort of the nature of what's observed to some degree, whether the particle has a position or a momentum. Sort of naturally begs the question, well, what is an observer then? And where does that come from? So I don't know if you want to go there in this discussion. I'm sure that is something we could spend a whole other hour talking about, which maybe you already have.
I'll give you a one-sentence answer of mine, because I don't think we do want to belabor it. You can build some sort of measuring apparatus, which, or a Geiger counter or something like that, which could go click, click, click. And for most people, that is sufficiently complex that they would regard that as an actual measurement. But of course, if you're a purist and you believe quantum mechanics applies to everything, the entire universe, then no measurement ever really takes place, and that the only way of reconciling that with reality is to assume the many universes, many different versions. I personally don't like that, but I also don't want to appeal to consciousness explicitly to bring the thing to a conclusion. I think we need to build consciousness in somehow. If quantum mechanics is a theory of the whole world, it should include consciousness, but not just as something to terminate the chain in the manner that von Neumann and Wigner liked.
Yeah, I would agree with that. I mean, to build a theory out of measurement doesn't seem to make any sense, even though that's the dominant view of quantum mechanics, so-called Copenhagen interpretation. I mean, what counts as a measurement? Is it us having to be there? Could it be a fly in the room, on the wall, or you know, a piece of equipment that we had left lying around? In the end, we are also part of the universe, and we also have to be described by quantum mechanics. The only problem, so that seems to lead us to many worlds, but which is a viewpoint of quantum mechanics that does not privilege observation. But on the other hand, many worlds has some deep technical problems as well. In particular, it's very difficult to define what we mean by probabilities. If everything happens, if you're in a world where there's a coin that's heads and a coin that's tails, in what sense is it 50-50 that the coin was heads or tails? So the key strength of quantum mechanics, which is that it can make these statements about probabilities, doesn't seem to make sense in a world where everything happens.
Great, thanks for that. So I'm going to switch to some questions that we received earlier before we started. So I think you may have touched on this already, but the first question that I have is, does reality exist if we don't have a mind? So we're going to try to steer clear of consciousness too much, but we can start there. And if you don't want to go there, there's another question from the same person, which is, what is the emptiness of reality? Which I think we can fairly concretely answer.
Yeah, I think if we don't have a mind, I would say that there's still a world out there, even if there are no observers. But it's less than real in the manner I tried to indicate. It's not the 19th century version. It's not a scaled down version of the everyday world. But nevertheless, that's not to say that there is nothing there, even if there are no observers, no minds.
Great, thanks. Maulik, do you have anything you want to say about what is the emptiness of reality?
No, not particularly. There are many other questions here. Yeah.
Sure. Well, here's a few more that we can go to. So when a particle is in a superposition, what chooses which outcomes are real? Are they all real, or at least to some extent? And is there anything properly real before it is observed?
So I think Maulik already dealt with that a moment ago.
Yeah, I can say a little bit more about something. There's a phenomenon called decoherence. And so, well, there's a famous example of a particle that's of a cat, Schrödinger's cat, in which the cat is both dead and alive in a way, because it's in both those possibilities. In reality, a cat would never be like that, because the cat is a macroscopic system that would be entangled with other particles and would decohere. What that means is that the cat would not be both alive and dead. It would be alive or dead, as we would expect from a cat. So that's the good news. The decoherence solves that problem of being both alive and dead, and replaces it with both alive or dead. But what decoherence doesn't solve is a fundamental question in quantum mechanics: is who decides whether it is alive or dead, and how do we go from those probabilities of being alive and dead to an actual realization? So The decoherence is, in layperson's terms, is an interaction in the environment. So a realistic system cannot be fully isolated from its environment.
Great, thanks for that. And I think that actually addresses another question we had in the chat about Trinity's cat. So that's perfect. I'm going to switch back to some more questions that we received via email.
Whilst you're doing that, let me tell you that I was once doing a TV show trying to demonstrate Schrodinger's cat with the studio cat. And we had a big box. And this little pussy was very docile and so on. But when you do anything in television, they say never work with children and animals. You have to do so many retakes that by the time we'd stuff this poor cat in the box, for the 10th time, it very, very definitely making a live sounding noises.
That's great. So here's a question that I think is interesting, but is perhaps too open-ended. So somebody's asked, what isn't reality?
The complement of all things that are real. Well, yeah, I did touch on this earlier because I said, I think, agree with Maulik that not everything that can exist, that is logically possible to exist, does exist. And so we can imagine, sometimes I show a slide with two great big urns, and one urn contains all of those things which are possible and which actually exist, and the other urn, which is probably much bigger, contains all those things which might have existed, but as a matter of fact didn't. And so if you imagine that less than everything exists, then there's a whole lot of stuff that is logically possible, maybe physically possible, but simply not out there anywhere.
That's great. So I think this is related to a couple other questions from the same person. So I'm going to say, let's see. So Paul, you were mentioning, things that could have existed, but as a matter of fact, do not. There's a question here about how you would describe time in that framework. And I mean here, time as past, present, and future. Can someone live in his future and present at the same time? And can those things be combined together? So it's quite the question.
Well, it is. And we could do an entire, if we didn't do it already, ask a physicist on what I would call the myth or the illusion of the flow of time. So like most physicists, I have what is sometimes called the block universe view, that the timescape is there, just like the landscape is there. It's all there all at once. So that this notion that we are moving through time, or time is moving, or all these confused metaphors, I think is an illusion. It's a mistake. It doesn't happen. And so I think the question was, can you exist in the past and the future? Is that?
Yeah.
And the operative word is you, because you see, we have this notion that we have fixed identities, that I'm a particular self, Paul Davies, I always was me, I always will be me, and that over time the world changes around me. But what actually changes is me. My brain states change. There's a strong correlation between my brain states of yesterday and today. A lot of mutual information, we would say, technically. But I'm not the same person today as I was yesterday. And the fact that it's not time that's changing, it's the personal identities that are changing. But we invert that and have this illusion that we're sitting in some sort of flowing stream of time. I don't think we are at all.
Great, thanks for that. So this is maybe following off of that, based on the discussion we had about, the way in which the choice of observation changes sort of, at least partially, the nature of the reality that we observe. Somebody has asked, I'll paraphrase here, since our observations, or at least our interaction with reality is creating reality, is it possible to erase what I created? And so we can answer that in a fairly simple question of, if you perform a measurement, that sort of tells you something about the properties of that particle, let's say. Yeah. Is there any way to undo what you've done?
There's a famous experiment called the quantum eraser experiment. Maulik, do you know about that? I was going to say, do you want to describe that briefly?
No, I don't.
Right, we don't have to. I mean, you need a diagram really, but no, it is indeed possible to not bring the measurement to a total completion and undo it and erase it. It's literally called the quantum eraser experiment. It's done with lasers and mirrors. You know, it's all done with mirrors. Smoke. So whoever asks the question should just go to a search engine and look up the quantum eraser experiment.
Great, thanks for that. So then there's another line of questions that's about energy. So the first one is, what does energy have to do with reality? And in reality, where does energy come from?
That's an easy one to answer because the total energy of the universe is 0. So it's not a problem. And why is that 0? People think, well, how can it be 0? And the answer is that gravitational energy is negative. You think about this, if you wanted to pluck the Earth out of the solar system, you'd have to do some work on it to pull it away against the gravitational pull of the sun. And so you've got to put energy in to take a gravitationally bound system apart. Well, the whole universe is gravitationally bound, and you can tot up all of the energy, negative energy of all the particles in the universe, all the stars pulling on all the other stars and so on. And when you do that calculation, convert it into units of mass, because E equals mc squared, so we can put it in units of mass, you get about minus, because it's negative, 10 to the power 50 tons. That's the number. And then you say, well, but what about all the positive energy, all the matter that's out there and the fields and everything else? And you add that all up and you get also about 10 to the 50 tons. So the two seem to cancel and give something very close to 0. And it's a puzzle. It's been a puzzle right back since the 1970s when cosmologists noticed that the universe seemed to have this weird coincidence that all the pluses and minuses cancelled each other. But we now have a good explanation for it. It's called the inflationary universe scenario. And it deposits the universe on a trajectory that is precisely on this line of 0 energy. So there's not a problem about the origin of energy because total energy is 0. That's not to say that the universe is explained. All I've told you is the energy story, but you can still ask, why did inflation happen and where did the laws that govern it come from and all the other features. But energy, don't stop worrying about energy. There's not a problem with energy.
Great. Let's see. Right, so there's a few more questions that we received by email, but they're mostly to do with consciousness and they're quite open-ended. So I think we can ask a few of the other ones that have been asked in the chat and circle back to those if they sort of come up. So somebody in the chat has asked, what does the necessity for imaginary numbers in quantum mechanics tell us about the nature of reality, if anything?
Yeah, it does. So Dirac showed that it's not possible to formulate quantum mechanics with real numbers only. Complex numbers are totally fundamental to it. And so the properties, I mean, I don't happen to remember which experiments would be different, but definitely experiments, the results would be different if you just had real numbers. It's interesting.
Yeah, it's very strange that unlike classical physics, which entirely seems to be real, in quantum mechanics, we are forced to use these imaginary numbers. And I think it has something to do with time, actually, that if you try to formulate quantum mechanics without imaginary numbers, you would.
If there are any,
you'd get a time spectrum.
Sorry to interrupt. If there are any people out there who are simply not physicists or mathematicians but find all this stuff entertaining, just a word of caution. When we talk about imaginary numbers, we don't mean, well, we're just imagining them. It's just a term that is used for numbers like the square root of -1, which don't exist in the usual number system that you're familiar with. But you can extend the number system to include those, and we call them imaginary numbers, and they're critical in quantum mechanics.
Great. So here's a fairly technical question that might be outside the scope, but why hasn't Rich Richard Harth has asked, why hasn't Bell's findings put the hidden variables argument to rest? Maulik, I'm not sure if you have something to say there.
Yeah, it kind of has in a way. There are a few loopholes in the argument, and mainly the precise statement is that there are no local hidden variables, which means that there's no little property that you can attach to the electron and say, oh, if we only knew that this was a blue electron, then we wouldn't be able to tell exactly what it was doing. But there could still be non-local hidden variables, and the argument doesn't eliminate those. I find them very unlikely, but they're mathematically a possibility.
Great, thanks. So Paul O'Brien has asked, when it comes to observations, is it not horizons all the way down, a 2D surface to observe?
Horizons all the way down. So this is a reference to the holographic principle that
I think it could be.
Is that, am I interpreting that correctly, do you think?
Maybe. So on that, I can say something that there's in string theory, there's an idea that that the world has fewer dimensions than meet the eye. So we think we live in a 3-dimensional world, but it might actually be just 2-dimensional. But you can't, and the basic dictionary is that a world with gravity can be mapped to a lower dimensional world without gravity. But that lower dimensional world cannot itself be mapped to a yet lower dimensional world because it doesn't have gravity.
And all this is an extension of Stephen Hawking's discovery that the surface area of a black hole, its horizon area, is a measure of its entropy, which is like the total information that it contains. And so if you can capture all the information in a 3-dimensional volume on a 2-dimensional surface, maybe that's a deep principle that applies to the whole universe. Or maybe not, but it's a popular idea.
Great. So Joseph has asked, at times, quantum mechanics sounds like subjective reality, meaning one person sees a tree fall and the other doesn't. Is this accurate? Subjective truth, where does it fit into quantum mechanics, or does it?
No, I think if I make a measurement of something, so the position of a particle, and then you make a position measurement of the same particle, you get the same answer. But if I measure the position and you decide to measure the momentum, I can't tell you what you're going to get. And so consistent measurements, you get consistent histories if you make consistent measurements. But if you make conflicting measurements, but you can't do it at the same time. You can't say, well, you measure the momentum of this electron and I'll measure its position. We get in each other's way.
Great, thanks for that, Paul. So related to that, which I think you both sort of addressed, but maybe is worth one more stab because it can be an unsettling topic on first encounter. Alina has asked, could you please explain the uncertainty principle in simple words for both representations, position, momentum, and energy time, and any analogy you have for real life, which is a difficult thing to find an analogy for quantum mechanics in everyday experience.
Niels Bohr always wanted to do that. He felt, so uncertainty is one aspect, so complementarity is the other, that there are complementary ways of looking at things. You choose to look at the position or you choose to look at the momentum. They're complementary variables, but you can't have them both together. They're not contradictory, they're complementary. And he always felt that there should be examples in human affairs that satisfied a similar sort of dictum, that it is difficult to find such things. But I think, the uncertainty, the position momentum, uncertainty principle, very simply, it just says that if you measure the position precisely, you're completely uncertain about the momentum, and vice versa. But if you make a less than precise measurement, then you can have a bit of both. And all of this is quantified. A lot of people think, oh, quantum mechanics talks about uncertainty. We can't trust anything. Science is full of uncertainty. Quantum mechanics precisely quantifies the amount of uncertainty. It's a precise theory. It can tell you the betting odds very precisely. but it can't tell you the actual outcomes.
Well, I have I have an analogy, which is actually a real life analogy, but it's not really the real thing, of course. So if you have a motorcycle going by and you take a picture with a slow shutter speed, you're going to see a blur in your picture where the motorcycle was, and that's going to give you an indication of how fast it was going, but not where it is. On the other hand, you can take a very quick picture and then you'll see exactly where it is, but then because it looks frozen in time, you won't get a sense of how fast it's going. So seems to be a trade-off between position and momentum. In the case of a motorcycle, that's not really, it's just this is just an artifact of the way we chose to measure it. The motorcycle very much does have a position and a momentum. For electrons and for quantum particles, the origin of the uncertainty principle is really the wave nature of particles. So if you have a wave, then a wave has a definite wavelength, but it doesn't have a definite position. You can't say the wave is right here because the wave is spread out in space. And to make the wave more localized, you can start adding up its wavelengths and have waves of different wavelengths. And if you take a bunch of those, then you can make the position sharper. But the price of that is that now the wavelength isn't well defined because you have a range of wavelengths that you use to make the wave compact. And for quantum mechanics, these wavelengths are related to the momentum of the particle. So there's a trade-off between building something that has very sharply defined wavelengths or momentum and very sharply defined position.
Great, thanks. Let's see, so we only have time for maybe one or two more questions. So I'm going to go with a question from Barbara that says, what if you tried measuring entangled particles? Would you be able to measure the momentum and position of both, or would they behave as if two measurements were being made on the same particle?
Right. So that refers to this Bell type setup, and you can measure independently on the particles a whole bunch of different things, and what happens is you sit down after the experiment is done and compare what you got over here and what you got over there, and that's where you find these correlations which are impossible to explain by any local real theory. That is, any theory of local interactions in which the particles really do have certain properties prior to your measuring them. Maulik, I don't know if you want to add to that.
Yeah, so if you have two particles that are entangled, it sort of means that it's like two coins whose, if you flip one and it's heads, the other one will always land tails and vice versa. So if you measure the position of the momentum of one particle, say, you will know that with 100% certainty the position of the other particle. But if you measure but if you measure the momenta, then you actually don't know the position. So although you can learn things about the other particle, there's no way to avoid the uncertainty principle here.
And in particular, you can't send information faster than light. This is a common.
And by the way, this was what Einstein, his most cited paper was the Einstein-Podolsky-Rosen paper, in which he tried to set up exactly this kind of situation where you have two entangled particles, you measure the position of one and therefore know the position of the other. And then Einstein said, well, that particle is so far away, you can't possibly have affected it. So now I'm going to choose measure the position, the momentum of the other particle. And since I already know the position from the first, from having measured the first particle's position, then I'll know both the position and the momentum of that particle. But that argument was flawed.
Well, I think it's always good to end on things that confused Einstein, because they can still confuse us today. So I didn't get to all the questions in the chat and some of the ones on the email. I hope you'll forgive me for taking some liberties in the topics. Many of the ones that
I'd be happy to type up some responses to a few.
Yeah, we can attend to those tomorrow.
Yeah. Well,
yeah, that would be great.
This evening.
I tried to aim for the questions that were hopefully of the most interest to the topic at hand. If you think that there's interesting topics that you haven't heard about, there may be more ask a physicist in the future. So feel free to email suggestions for topics that you would find interesting to hear about. And with that, Paul, I don't know if you have any closing remarks.
No, it's just, it's been another fun season for doing Ask a Physicist. I hope everybody had a great Thanksgiving and you'll have a great holiday season coming up and a wonderful new year, as COVID-free as we can hope for. And we'll be starting up again in January. And I think we would like some feedback from our audience to know whether we could do things a bit differently. We don't have to have two presenters. We could have some guest speakers. We could have panel discussions. Or we could just go the whole hour with the Q&A. But we would like some suggestions for topics because we've covered a lot of things and we're sort of beginning to run out of profound topics. We like to have things which are on the conceptual edge, if possible. So if you can leave, Jessica, if you can leave the link open, then Maulik and I could maybe type a few answers. Or is it going to drop out?
No, I can leave it open.
I'm typing questions to responses to questions.
Because then that could be dealt with very efficiently. So I'm happy to spend 5 minutes doing that. But everybody else can go if they've had enough.
Okay, then I will leave it open.
What happens if Maulik and I are trying to answer the same question at the same time? Oh, I see. It
will show both of your answers.
Any comments on Boltzmann brain? Okay.